Good morning, everyone, and thank you for joining us for today's webinar. My name is Jean-Pierre Picard. I'm Product Marketing Manager at CM Labs, and I will be your host today. With me on the line is Marc-Alexandre Vizina, Product Manager for Vortex Studio, CM Labs' software platform. And he's going to be walking us through a very interesting project today. We're going to look at how we've created a driver trainer demo for a recent trade show to which CM Labs participated, which was ITSEC in Orlando. So before we get started, I'd just like to mention that this webinar is part of our Vortex University webinar series. Vortex University is a monthly webinar series in which we present a specific topic and we go in depth. We go beyond your typical, new features, product release webinar, and we look at specific challenges and features that can help accomplish a certain task. We've had about 8 webinars this year, and you can keep track of all of them at cmlabs.com/vortexuniversity or view the archive versions on our YouTube channel. You can also keep track of the upcoming sessions at the URL on screen. So today's presentation will be split into 3 sections. We're going to start by having an overview of what the Vortex Studio driver trainer demo really was about, what we wanted to do, what the end result was, who was involved. Then we're going to look at the different expertises that were involved in the creation, and you'll see that there's quite a few expertises needed to create a really immersive and realistic driver trainer simulation. And finally, we're going to look at a few of the specific challenges that were faced during the project. Now, the presentation is available on the handout section of the GoToWebinar interface, so feel free to download a copy to refer to it after today's demo. We will be sending a recorded video of this presentation by email as well, so if you miss any segments or you want to share them with some of your colleagues, that'll be easy as well. If you have any questions, I invite you to use the questions box also located on the right-hand side interface of the GoToWebinar interface. Before we jump into today's specific content, if you're new joining us because you've met us at ITSEC, just a quick reminder, what is Vortex Studio? Vortex Studio is a unified visualization and simulation platform that's used for virtual prototyping, operator training, and operational planning for land and sea equipment. Now, Vortex Studio provides you all the tools you need to create, integrate, and simulate land and sea vehicles, and we're going to look exactly at what those tools are today. Vortex Studio is used in multiple industries. It's used in construction, maritime, defense, and it's used across the world by customers in over 35 countries. And it's today powering over 1,000 simulators, making it one of the leading platforms for land and sea simulation. The application we'll be using in today's presentation and screenshot is called the Vortex Studio Editor. It is the desktop application that's used to create and validate virtual interactive equipment and scenes on final hardware. We won't be looking at the Vortex Studio Player, which is used to distribute the simulation content over the network, because we'll be using a desktop simulation environment today. All right, since we have a lot of content and we might actually be running short on time at the end of the hour, we're going to dive right into it. So let's talk about the driver trainer that we created for ITSEC. Now, Marc-Alexandre, could you tell me a bit about what the goals of this driver trainer was?
Certainly, GP. So for the show, we had a couple of. So the first one was to allow the tire models to be experienced by people. So basically, it's something that we brought in on Vortex 6.8, which allows you to simulate tire contact with the ground. The second thing we wanted to showcase is the latest visual that we've added to the editor. So now we support what we call vegetation field, which is a procedural tool that allows you to put vegetation over a large area. Also, we recently added multi-texturing, masking, and a couple of other graphics tools, and we wanted to showcase them to the public. And last but not least, we wanted to prove that you could develop an entire simulation starting from the 3D model through mechanical engineering all the way to deployment on actual hardware using only the Vortex editor, the Vortex player, and the Vortex SDK. So only the desktop app that are part of the Vortex Studio suite. So the team that worked on the project was composed of several specialties. The first one was the 3D artist, whose responsibility is to create the 3D model, import it into the graphic gallery format, edit the graphic material, so adjust the reflectivity, the shininess, the exposure, and so on, and also provide support for the rendering effect, so the shadows in the scene, the overall color balance in the scene, and so on. The second team member was the mechanical engineer, so he's responsible for the mechanical dynamic of the vehicles, the control logic and scripting for the operation of the vehicle, and the input-output connection to the actual hardware. The third specialty is the scenario designer, so they create the scenario and define the various events that are going to be experienced by the driver. They suggest asset placement and instancing over the entire scene. They also, in conjunction with the 3D artists, prepare the level of details and the special effects, such as smoke and other particle effects. They also place the vegetation, human figure, and the digging zone if these are required by the scenario. And last, the system engineer is responsible for putting together the simulator configuration file and also to integrate the hardware for control and motion. So the simulator hardware that we use at the show both had a motion platform, so it's important to have somebody who make sure that they run completely. The system engineer also ran some debugging and profiling tool to help us with the optimization of the scene to make sure that we get good performance out of the hardware. Now, all of these specialty tend to use one type of file in Vortex. So the artist is in graphic gallery, the mechanical engineer is using the mechanism, the scenario designer is mostly going to work in the scene file, and the system engineer is going to prepare a configuration file using the setup editor. You'll notice that all of these are part of the Vortex scene, so it means that we can work as a team in parallel. It's possible to have a concurrent content workflow. So while the 3D artist was preparing the model, the mechanical engineer was using a placeholder model to start building the dynamic of the vehicle. Meanwhile, the scenario designer was able to use boxes to just start placing elements in the scene, and the system engineer was writing the configuration file at the same time. So this saves a lot of time and effort in leverage a synergy in the team where each can help the other solve problem. The vehicle that was chosen for the demonstration was the Oshkosh M-ATV. It's a mine-resistant armored vehicle that's been deployed by the United States Army as well as several allies in the Middle East and other locations. Now we've selected the M-ATV for a couple of reasons. The first is that there's readily available data on it, on performance, mechanism, structure, and so on. Also, the controls are familiar. It's a truck, so it has steering, gas pedal, brake pedal, automatic transmission. So for most users, they would just jump right into the simulator and start driving it, which is perfect for a trade show. Finally, it's a great showcase for advanced mechanical modeling. The M-ATV is equipped with a very complex suspension system with a lot of motion up and down, spring, hydraulic, pneumatic suspension where you can adjust the tire pressure of the wheel. All of these were modeled in the Vortex mechanism. The scene itself, so we had a couple of requirements. First, the scenario had to be of a short duration. It's a trade show. You want people to go in and out of the simulator so that we can maximize the number of people who are able to experience Vortex. The second requirement is terrain variety. So we really want to show that Vortex is able to handle a number of different terrains such as asphalt, rough ground, even water fording. So we prepared a terrain that's not a real-world location, that's adapted from a real-world location, but also has a number of elements to allow us to compress the experience in a short amount of time. Finally, we wanted to show a normal operating environment for the simulated vehicle. So we made sure that we had as many items to interact with as possible. To give you an example, at the start we're in an airbase. So there's buildings, there's other vehicle, equipment laying about, all of it on an asphalt or hard ground surface. Then we move out of the base into a muddy road. so it's a lot more slippery, and that's where the tire model really shine, and also allow us to display the vegetation field to their best effect. Then we get to the river. The river has water in it, so we're able to cross and ford it with the vehicle, so it's a different aspect of driving. Also allows us to showcase the particle effect. And finally, we go into a typical Middle Eastern or Afghanistan city with buildings and streets and numerous elements in it. The hardware platform themselves. So we were using two different platforms. The first one is a Doron 550 Truck Plus truck simulator, which was provided by Doron Precision Product, which is one of our partners. The specification, it's a 3-screen setup, landscape mode, a CAN bus steering wheel with force feedback, so when you're turning you can actually feel the resistance of the wheel. The entire cabin is mounted on a D-box actuator, so you get some vibration and some movement as well. And finally, we also have a hardware dashboard, so gauge and needles are actually moving instead of seeing the information on the touchscreen. On the other side of the show floor, we also had a Vortex Advantage platform deployed. The Vortex Advantage is our new simulator product that is able to be bought off the shelf. The Vortex Advantage features 3 screens in a portrait mode, so the screens are placed vertically instead of landscape. It has a CAN bus steering wheel without force feedback. It also has D-box trade-off motion platform, but this time with a 2nd generation actuator. So this one has a lot more motion than the previous cabin. It doesn't have an actual hardware dashboard, so it's using a virtual dashboard placed on the touchscreen that's actually hidden behind the gentleman driving the simulator right now. So if we see the simulator in action, so here I'm driving the Doron 550, and I'm crossing the airbase. Now I'm crossing the city, so you can see the field of view is fairly restricted in our armored vehicle. You can see the hardware as well. Some scripted elements are available. You saw me change the tire pressure with my right hand using the hardware control. We're also going to be crossing several different environments. So here we're going into mud and driving down to the water. I'm adjusting the pressure again. This time I'm crossing the city. You can see an urban environment with fairly tight streets, and I'm driving through. And now you're going to see something interesting, the interaction of tire models slipping on asphalt, contact physics with the curb, and a very bad driver. So flipovers are common using these big top-heavy vehicles, and I experienced it firsthand. So we're going to switch to the next file. So the project itself. So the project stages. First, we started with brainstorming the scenario that we wanted to present based on the requirements that we had. Then we went into an execution mode where in parallel we did the 3D modeling, the mechanical modeling, the level design, the integration of the simulation on the hardware. And then in a loop, we went into a troubleshooting and optimization period. So every time we made major changes, we went back to the hardware, made some tests, optimized the simulation to make sure it would keep on running at 60 FPS, that would be easy to understand and would provide an interesting experience to the user. And once this was done, the simulation was deployed on the 2 simulator platform for shipment to the trade show itself. Let's take a look at each stage of the process. So the first one is the 3D modeling of the vehicle itself. Again, I want to remind you that even though I'm presenting them sequentially, they were actually done in parallel. So that's fairly important. So the modeling of the vehicle is done by the graphic designer. The vehicle itself is built in 3ds Max and imported in the graphic gallery file in Vortex. In our case, we used a DAE file format to export the model, but there's also support for OSG, IVE, FLT, and even the leading CAD file type. So if you have access to a CAD model of the vehicle you want to model, it's possible to import it if you have the proper license. Now there are 4 steps that we use to create the vehicle model. First is contour block, then rough shape, exact shape, and then texture. What do these mean? So first we do a basic model, which is just the contour block. So the dimension of the vehicle are accurate. The wheel are just plain cylinder of the right width and diameter. And this is provided to the mechanical engineer because that's all they need really to get started on the mechanical modeling. They can define the position of the wheel, of the chassis, start to input engineering data such as engine performance, transmission setup, steering, and so on. Meanwhile, the artist goes back and starts creating improved shape. So we have a better idea of the shape. This goes back to the mechanical engineer to test the collision and the clearance. So we're refining the collision geometry around the model to make sure that we have the correct volumes. Then the artist finishes the work. We have the exact shape and volume approval. The entire team looks at the model, makes sure that everything is correct, all the parts that we need are there, all the transform are in the right place. The node list, the hierarchy is logged down and final, and this allows the mechanical engineer to go in and finish modeling the entire suspension, which you will see later in another slide. And finally, we get the texture. So the model is textured and colored. Level of details are set up for the scene. So level of detail allow you to have a less detailed vehicle the further you are, so it saves on memory and rendering time. This is provided to the mechanical engineer. Integration is very easy. We just replace the graphic gallery and reattach the various parts. You can learn more about level of detail in our Vortex 6.8 webinar. It's a fairly new feature, which would be a bit too long to explain here, but it's very useful. So I invite you to go to our YouTube channel and check the related 6.8 webinar. 3D modeling of the scene. So the scene itself is defined by the level designer. It's created by the graphic designer, however. It's built in 3ds Max and imported into a graphic gallery. So at first we start with just a rough layout. So the roads, just a rough idea of what the terrain will be to allow us to test the duration of the scenario and also identify any pitfall that we might have. Then we place the main objects in the scene, then the secondary object, and finally we do an optimization pass. So the rough roads version, we have the proper terrain material, we have the road itself. You'll notice that the city and other items are just blocks for the most part. So the idea is to just have key items to navigate around. So this is to test mostly tire modeling and adjust the various parameters of the tire model to make sure that we get accurate response and reaction from the vehicle. Then we start placing the main object. So we have a number of building models that are prepared. We update the road based on the preliminary driving test, and we add the large object to the scene, so the various big building. It's also at this stage that we place the vegetation field, and we adjust the density for both looks and performance. So the vegetation field is a new tool that's coming in Vortex, the next release. So it's a procedural terrain tool that allows you to populate an area of the scene with vegetation without having to put trees individually. So this speeds up the scene creation considerably and also allows you to place not just trees but also grass, bushes, and even graphical objects such as rock. It doesn't allow you to place mechanical object yet, but at some point that feature is going to come. Then we go and we place a secondary object in the scene. So these are visual elements without collision geometry. Sometimes we also place additional collision geometry based on user testing. So what this means is that some of the objects are outside the driving area. So they're there really just to put, to give life to the environment. Also, some of the objects have to interact with the user. So in this case, the barrier, for example, in the upper image are there to prevent the user from going further down the street, whereas the tank below is actually outside the drivable area, so it's just a graphic model. It doesn't have collision geometry. Finally, we go and we optimize the scene. So we separate the various area in multiple graphic galleries, so more than one person can work on it. In our case, what we did is that we had one graphic gallery for the airbase, one for the city, and one for the countryside. And this allowed multiple persons to work in parallel on them to optimize the texture and also to adjust the level of detail based on what we could see from the truck itself. The texture optimization, basically we went all with models that were featuring fairly high-level texture. Once we went into the driving scenario, we took notes of what's available and what's visible from the truck cabin, and objects that were further away from the truck were noted down, and then we went back in the graphic gallery and we reduced the size of the texture to reduce the memory footprint. So we went from a graphic gallery that was 283 megabytes to a graphic gallery that was only 7 megabytes, just by reducing the texture, eliminating buildings and items that were not visible from the truck, and so on. And this is a major improvement on the scene itself. Finally, we also put in the level of detail configuration. So level of detail, what it does is that it allows you to specify when an object will appear, will be visible, and also how, what kind of texture is going to be used and what kind of mesh is going to be used for the model. So this is done in order to save both memory, because you don't want to have models in memory that take up a lot of space, and also to save on rendering, because you don't want to have items displayed that are just simply not visible by the user. So now I'm going to go and switch to the Vortex editor itself. And I don't know if you guys can see it. So this is the scene in the Vortex editor. So this is the starting area. So you can see our little truck here with the blue rectangle is actually the viewport. So that's the viewpoint is used for setting up the hardware later on. So we have the various building here, and you can see the green boxes at the back. Those are actually the various vegetation field that are used in the scene. So once you move through the scene, you can see that there's not much element down here. That's because they're simply not visible. When you're driving the truck, you're seeing it from this perspective, so you don't see any buildings. So there's no point in putting them in the scene because they're simply not going to be visible. And then we go up to the entrance of the base, and then there's a second vehicle that's present there. So that's, you'll recognize the MATV with all the suspension model. And that's actually a computer control vehicle that's going to lead you through the scenario into a convoy, and that you follow it through the scene. And let's see if I can make my way to the river. There we go. And there we go. So we have a human figure that's blocking the way, and we have a truck that's been destroyed and that's sitting on the bridge, and that forces us to go down into the river here. And you can see the level of detail here. You can see the bridge appearing and disappearing as I move my camera. So there's it's a fairly large scene, 1 kilometer per 2 kilometer. It stretches the limit of the technology that we're using in Vortex for terrain, but it's still quite usable. So if we go here, and we see here, and we have the wall of the city, and then we find ourselves in the city, and you can see the level of detail again, making buildings disappear as I go further down from them. And then as you get closer, the building actually appear. And they'll fade in and out from view as needed, depending on where you can see them or not. So let's go back to the slides.
Right. And I'd just like to take this occasion to mention that you can send us your questions at any time during the presentation, and we'll have a live Q&A at the end of the presentation. Back at you, Marc-Alexandre.
Thank you, GP. Let's switch to mechanical modeling of the vehicle itself. So this is accomplished by the mechanical engineer and using the mechanism document type. So the steps required: first, we set up the parts and constraints that make up the vehicle. Then we set up the powertrain, so the engine, the transmission, the suspension, and so on. Then there's a new step, the tire model, where we set up the various parameters that are featured in the tire model component. And finally, we use scripts to set up the various control of the vehicle. So first, we set up the collision geometry. The hull itself is a part with a convex shape placed around it. We were fairly generous with the collision geometry. There is no real purpose into having something that closely conformed to the shape of the vehicle itself. As long as it's reasonably close to the hull for a driving simulator, it will be enough. The wheels themselves were set up via the vehicle system. So we created a specialized template. I'm going to talk about it a little further. But first we had to set up some constraint for the turret, and that you can see here, so that it can pivot. In the end we didn't use it, but it's set up to pivot. And also we had to set up all the various constraint inside the suspension, so that we would have a suspension that would actually be working. So we're not just relying on the vehicle system, we actually set up constraint for all the suspension parts. So the arms, the spring itself, the various shock absorber, and so on. Then we did the custom preset vehicles. So there's a number of vehicle preset that comes with Vortex. You can see a list here. So we've slightly modified one into a 4x4 configuration with a manumatic transmission, which is a type of automatic transmission that you can override manually. Then we went and set up the tire model for the vehicle. So we had a number of ground types that we would be crossing over, so asphalt and hard ground inside the airbase and the city itself. Then a wet road, a muddy road on the way to the river, dry mud on the riverbed, shallow water for the ground underneath the water, and then grass in some area as well. So we needed to prepare a tire model for each of these contact material. You'll notice that there's a few more, such as ice and snow, that we didn't bother to set up, but they're still present in the MATV tire collection, just in case we need to use them in another environment. Because, of course, once the mechanism is prepared, you can reuse it in something else. So there's a good chance that you're going to see that MATV again. So the tire model, we're going to have a webinar later on this because it's a complex subject all of its own. What it is that it allows you to attach parameter to the tires to define the contact between the tire and the ground, either as hard material, so asphalt and packed ground, for example, or soft material, such as sand and mud. Now, the tire model take tire pressure into account, and also a number of other coefficient and parameter that are usually defined experimentally in the laboratory. So if you have access to these parameter, you can insert them into the tire model of your Vortex model and have increased realism in your driving experience. So you remember that you saw me earlier flip the vehicle in the video. That was caused by me taking the turn too quickly, and the tire actually slid sidewise on the asphalt. So that's not a behavior that's easy to reproduce using just basic contact physics, but with tire model it takes into account all the forces and all the deformation, so the vehicle actually slid to the side. So you can do fishtailing, you can do wheel spinning. It's something that we saw often as well when people were trying to get up the riverbank. They went to the other side, just pedal to the metal, and the wheel would just spin and throw off mud, and the vehicle would go absolutely nowhere. So it increased the realism of the driving experience, and while it's a lot of work to set up, it's usually very worthwhile. Next, we put together the control script in Python to control the various systems of the vehicle. So that included the transmission logic for the pneumatic transmission, traction control system to emulate what's on the real vehicle, and also a tire pressure system, again to emulate something that's available in the real vehicle. And we found that the tire pressure system actually came in really handy to get out of mud in other hard to reach areas. So we had 4 different settings. So highway, which was 2-wheel drive, high tire pressure, cross-country, which was 4-wheel drive, lower tire pressure, and even a mud mode with very low tire pressure, locked differential to allow us to get us out of a hard situation. You can see on the right-hand side of the image the pneumatic transmission board. On the Doron truck simulator, this was actually a hardware piece because the Allison transmission is widely used on military truck in the United States. So we had actually a hardware control for this, which heightened the driver experience for those using the Doron system. You can also see the ignition key, parking brake. All of these, including the dials, are fully operational and emulate the dashboard of the real vehicle. Now, why did we prepare a dashboard like this? The reason is on the Doron system we had hardware dial, but on the Vortex Advantage, which has been created to be a generic platform, we had only a touchscreen, no actual hardware. So we created this virtual dashboard to be able to control the truck just like you would on the real vehicle. Now, we have a Vortex University webinar on vehicle component. If you want to learn more about how to set up your vehicle, I invite you to check out our YouTube channel, which is youtube.com/VortexSim, to check the Vortex University vehicle webinar for more information on how to create a vehicle. Next, we go to the level design. This is accomplished by the level designer using the scene document type. So again, we break down the work into several steps: scenario, scripted event, blocked off area, and ambient sound. First, scripted event are things that happen in reaction to the player's action. So in this case, for example, once you get close enough to the barrier would lift and let you through. This is an example of scripted event. This particular scenario didn't have that many of them, but it's possible to include a number of events in any training scenario to emulate a number of situations. Another example of a level designer task, blocked off area. So we're coming back to this image. You see those red barrier. The reason they are there is because originally the user is supposed to turn left into the street, so we just put the truck in the way and with the pole crashed over it, and we expected it to be enough so that to tell people, hey, you can't go there. But in training and in testing, we found that our QA guys would often go straight across the sidewalk and attempt to drive forward. So our level designer went back and he took 2 concrete barrier, put them in the scene in the graphic gallery, and then put a collision geometry over them to make sure that this street was blocked. So that would prevent the user from getting lost by taking a wrong path in the scenario. Finally, integration. This is accomplished by the system engineer. So they're using the setup editor which is part of the Vortex editor. What this does is it allows you to create configuration file which used to be coded by hand by the system engineer. So it's a lot easier now to do it through the graphic user interface. This was introduced in Vortex 6.8, so it's fairly new. The point-and-click tool to define network hierarchy and physical display allows you to just drag stuff together in the Explorer panel and set up your network topology to make it a lot easier to create your configuration. So you can see here we have the configuration file. Just going to close down a few boxes. This is the configuration file that was used for the Doron 550 Truck Plus simulator. So you can see that the 3 screens are placed here. That gentleman here is the our viewpoint character. So you remember when we were on the scene level, there was a blue square around the viewpoint of the driver. So this corresponds to this figure here. The screen hanging off in space here is a touch screen. Since it's bolted to the side of the cabin, it doesn't really matter where you put it in space because it's not actually showing the simulation, so it doesn't matter where it's placed. Now, by doing the display here, we're able to adjust the position very easily rather than having to go and code all the information into a configuration file. Now all of these modules here, so the network module, the loading image that we want to have, even the placeholder while the screen is loading, everything is set up through the editor here. And let's see if I can go and open the Advantage configuration file. So here we go. Let's just delete this. So the Advantage has a different screen configuration, so has a different configuration file. However, most of the information is the same. So what we did is that we prepared one configuration file for the door-on setup, and then we saved it, made a copy, and then we modified it to have the screen configuration for the Vortex Advantage, and we changed the module required. So that way, the design of the configuration file was a lot faster than the old method, which was just measuring everything by hand and then coding everything by hand. So I'm going to ask GP to go back to the slides. Thank you, GP. And so we did use the setup editor to set up the config file, but we also used the Vortex SDK to integrate the hardware control of the door-on cabin. So basically, the door-on hardware had an API that came with it, and we used the Vortex software development kit to write a small extension that will allow Vortex to talk to those hardware. And it was very successful. It was actually used in 2 projects, so we didn't have to redo it for this trade show. You can learn more about the setup editor in the Vortex 6.8 webinar, so I invite you to go to our YouTube channel and take a look at it. Optimization. The cardinal rule when developing a Vortex simulation: optimize early and often. You want to test on the actual hardware that will run the simulator. Don't trust the editor, because since the editor has a lot of content creation tool, has a very high memory overhead. So a scene that will run poorly in the editor may actually be running very nicely on the hardware, and vice versa. So it's very important to go not to test inside the Vortex editor or even the Vortex player, but actually go to the actual simulator hardware and test it over there. So to give you some ideas of what we dealt with on this project, a couple of the issues we encountered while doing the optimization. First one was the frame rate. So we put together the scene, the mechanism, the scenario. We brought this over to the Vortex Advantage, and we started running the simulation, and the frame rate was somewhat poor. So we're running at 20-25 frames per second, which is well below our 60 frames per second target. So we used the profiling tool to get an idea of what's going on. The physics was running fine. I mean, there was no delay at all. The CPU was supplying all the horsepower, so the problem wasn't there. So we dug a little further. We went into the GPU and we started looking at its load, and we realized that the GPU was actually quite overloaded. So we were using 4 gigs memory cards, and the actual memory footprint of the simulation was 4.7 gigs, which means that swapping was taking place, which would explain the low frame rate. So we went back to the scene to see what was causing this massive amount of information to be stored in memory. And then we realized 2 things. The first one is that one computer was running 2 screens, so it was actually holding every texture and memory in memory twice. So right there we see a major problem. Second, it's not normal to have a scene that's 2 gig in memory. So we went and opened up the graphic gallery, and then that's where we realized that some of the texture had not been optimized. So every object that was far away was just as detailed as the objects close to the driver. So a house in the hill had as many detail as a house close to the road. So we went back, we eliminated every model that could not be seen from the truck, and then we went to the textures and we set a number of distance, and every model in those range band, if you will, had its texture reduced from 2K, 1K, 512, 256, and even smaller as we went away. One graphic gallery went from 283 megabytes to 7 megabytes just by doing this cleanup. Frame rate went straight up to 60 FPS. We were very happy, but it shows you that it's important to optimize throughout the development of the simulation, not just at the end. It's going to save you a lot of headache, a lot of stress. Every time you make major change, you insert a new element, a new mechanism, a new graphic gallery, make sure to verify the frame rate, optimize right away. You'll save a lot of time and effort. Another problem that we encounter, the vibrating vehicle phenomenon. So when the vehicle is running, the engine is causing it to vibrate. And when we're driving over rough ground, the vibration is increasing, which is completely normal. Our problem was that when we parked the vehicle and shut it down, the vehicle kept vibrating, which is not a normal behavior in any way. So tracking down the issue, we started diagnosing, okay, is the engine truly shut off and not just the sound? Yes, the engine is shut off. Is the shaft too loose in the, did we put too much relaxation in the shaft? No, it's fine. Then we went and took a look at the suspension, and as you will remember, the suspension was composed of many elements all linked together by constraint. And what we found is that we had so many constraints so tight that the suspension was fighting itself, trying to get rid of excess energy, which was causing the vibration. So the solution was to identify a couple of key constraints and just put some relaxation in those constraints, not too much, so we don't want to have the vehicle too loose, but just enough so that the vibration could be absorbed by the structure. Our vehicle quieted down, that problem went away. Another problem that we encounter, excessive network data exchange, is something that our system integrator noticed, is that by looking at network tool, realized that a couple of megabytes were being exchanged between the node every second, which is not normal behavior again. So he went back to his setup editor and moved the assignment of a couple of the module inside the configuration to optimize their position, make sure that module that were talking together were put on the same computer to avoid sending the data over the network. This reduces the network transfer and actually saved us a bit of processing time, which in turn gave us a much better frame rate than we had before. So we had a couple of other problems, but they're fairly usual, just debugging, things that were forgotten, things that were added to the last second. But again, doing the optimization early and often saved us a lot of trouble for the final show. The Vortex University that we did in September, October, we did 2 of them on profiling, optimizing, and troubleshooting. So I invite you again to go to the youtube.com Vortex Sim channel. Check out the 2 webinars on profiling and troubleshooting. You'll learn quite a few of the tricks that we use to put together the simulation for the trade show, and this should help you avoid most of the most common pitfall that people are facing when they're putting together a Vortex simulation. Final result, stable 60 frames per second on both platforms, so on the Doron Precision product simulator and the Vortex Advantage. Big hit at the show. People loved driving the truck throughout these complex environments. But the nicest thing was that we received visits from Oshkosh representative and actual Army driver who piloted this kind of vehicle in Afghanistan and Iraq, and they tried a simulator, and they told us, you know what, guys, you pretty much got it. That's how the vehicle feels and drives. So that was something that was very good to hear from our visitor, and we really enjoyed doing that project for the trade show. So now I'm going to send you back to GP to wrap this up. And if you have any question, again, you can submit them via the webinar system.
Thank you, Marc-Alexandre. All right, so just before we move on to the questions, and I see quite a few coming in, I'd just like to just draw a few of the big conclusions from this. The first thing I think that's worth remembering is that this entire driver trainer was created using Vortex Studio, and it was done in a concurrent manner. So you get a complete simulation development environment, and that development environment really optimizes the process by allowing each of the different expertises involved to iteratively work on the simulation. That saves you a lot of back and forth later down the line. Now, the second thing to really remember is that you have a specialized vehicle simulation module that allows you to take engineering information and turn it into accurate performance. And again, getting Oshkosh representatives and driver to say this feels like the real thing when we didn't have access to an Oshkosh representative for the creation, I think is a testament to how powerful and efficient the platform is as with regards to ground vehicle simulation. So we're going to move on to the questions second. I'd just like to promote our next Vortex University webinar, which will be back after the holiday break on February 3rd, 2017. This one will be at 10 a.m. and we'll be looking at tire models, which is a major feature that was introduced in 6.8, which is covered partly in the 6.8 webinar, but it's really a long, complex topic that we could spend an hour on, so we will do exactly just that in February. So you can find the next session on cmlabs.com/Vortex University, but we'll also send you a direct link in the follow-up web email that will be sent in the next 2 days. So I'm going to open the floor to question. We have quite a few that are coming in. We'll be getting to all of them, so if you have questions and it takes a few minutes, don't worry, we're not leaving until we have answered you. For those of you who are leaving us, again, thank you so much for joining us, and we hope to see you in February for our next webinar.